Hello everyone, my name is Chandran Chakraborty from University of California, Santa Cruz, advised by Professor Heiner Litz. Today I'm going to present our work on reducing write amplification in Flash by death-time prediction of logical block addresses. In a log-structured system such as an SSD, data is not typically updated in place but appended to a log. The log maintains multiple versions of the same data, where the most recent version of the data is considered valid and the rest invalid. To bound the storage capacity of log structured storage, garbage collection needs to be performed to remove the overwritten data elements from the log. Garbage collecting a block requires copying all valid pages from that block to a new free block, and only then the clean block can be shortlisted for cleaning. This garbage collection process requires over-provisioning in SSDs to copy the valid data to new blocks when all the free blocks are extinguished. This extra writes results in reduced lifetime. During GC, it's also typical to see high tail latency, and as a result, cloud service providers are unable to guarantee an IO response time. As previously mentioned, GC is the process of recycling invalidated pages to free up space for new incoming data. The GC overhead can be measured using write amplification. Now, write amplification is the ratio of the number of pages programmed within the SSD to the number of page program updates issued by the host. And the magnitude of write amplification depends on factors such as the over-provisioning ratio, the mapping mechanism, and the write patterns. For applications that demonstrate sequential write patterns with uniform write frequencies across LBAs, write amplification tends to be low, as there is high probability that LBAs within the same block are overwritten with the same temporal proximity. However, for most applications, the write frequencies of LBAs follow a highly skewed distribution, resulting in an increased write amplification. We define death time of a data element as the number of I writes in future before the data element is overwritten. The key idea is to group LBs with similar death times together within the same block, and assuming there is sufficient number of concurrently open blocks, write amplification of 1 can be achieved, which is an ideal placement strategy. We introduce the basic operating principle of our death time policy with this example. In this example, we assume an SSD has a block of the SSD can have 2 LBAs, and we observe writes to 3 LBAs A, B, and C. The first row shows the elapsed time. The second row shows the LBA write sequence. Then the third row shows the corresponding death time of the LBAs. Rows 4 through 6 shows 3 block allocation policies, and each unique block is represented by a color, and the policies strive to use as few blocks as possible to store the data. Now, the fourth row shows how conventional FTL will absorb the write sequence, which has only single block. The first 2 blocks are written to an orange block. At time 3, the orange block is closed and the blue block is opened. At time 5, the orange and the blue closed blocks still contain valid LBAs, which you can see based on the death time information in the second row. As a result, the green block is open, absorbing the next writes. At time 7, the blue block can be reused as all LBAs have been overwritten. This policy requires 3 blocks to absorb the write sequence. The fifth row in the table shows the operation of a hot-cold based frequency block allocation policy. LBC is considered a cold LBA, whereas A and B are considered hot. As a result, at time 1, C is placed into the orange block, whereas A and B are placed into the blue block at times 2 and 3. At time 4, the blue block is closed and the new hot green block is opened. At time 7, both A and B within the blue block has been overwritten, which lets us reuse the blue block at time 7. This policy also requires 3 blocks to absorb the write sequence. The sixth row of the table shows how our death time aware allocation policy works. LBC written at time 1 and LBB written at time 3 have similar death times of 5 and 4 respectively, and hence are placed into the orange block. The LBs written at time 2 and 4 are placed in the blue block. At time 5, the death times of all LBAs in the orange block have elapsed, and hence it can be reused. Oracle DT minimizes the number of blocks in use, requiring only 2 blocks to absorb the write sequence. In this work, we make the following contributions. Firstly, we present a data placement strategy which can guarantee no garbage collection overhead, having perfect knowledge of death times. We also present a practical approach which uses machine learning models to predict the death times of LBAs and present the design of ML-DT. Finally, we experimentally show that our approach outperforms the best baseline technique by 14%. For this work, we leverage traces from 10 real-world workloads from 3 different sources. All the traces were collected at block IO level, and we can see the trace characteristics from the table. All traces were in general write heavy with greater than 0.5 read-write ratio. Upon analysis of the death times, we make the following observations. First, real-world workloads exhibited skewed write patterns, which you can see from the figure on the left, where a significant number of IO accesses are covered only by a few LBAs. As a result, the distribution of LBAs tend to have a long tail, as can be seen from the figure. We also found that the death times of LBAs tend to vary wildly from a few IOs to a few thousand IOs. Separating streams based on death times enables invalidation of pages within a block solely by user rights. We also saw that user rights originating from the same location and time tend to have similar death times, which is in line with prior work. Hence, IO rights can be used to separate streams of data with similar death times together within a block. Finally, we also saw that for a given LBA, the death time changes over time. Hence, prior history of assigning death times to LBAs can be inefficient, resulting in higher write amplification. For our work, we considered two features for input to our ML models, the LBA and the IO size. We separate each LBA into two parts. The upper and lower significant half of the bits are separated and hashed into value between 0 and 100. This allows the model to distinguish between the interleaved write patterns using the higher bits and predict within a stream using the lower bits. The LB is also, the full LB is also normalized between value of 0 and 1. In order to reduce the number of possible IO sizes, we round off each IO size to the nearest value of log of that number and use it as a feature. This reduces the number of possible IO sizes to 16 while still supporting request sizes up to 64 megabytes. The proposed model is shown in this figure. The inputs to the model are categorical one-hot representation of input values, which each of them are fed to a separate embedding layer for dimensionality reduction. The sparse embedding vectors are then concatenated and fed to a shared dropout layer to prevent overfitting of the model. The death time prediction of the model is performed by the temporal convolutional network layer, which is a variant of the convolutional neural network or CNNs. TCNs employ causal convolutions and dilations to learn from sequential data with temporality. Now, as TCNs implement a memory using the causal dilated convolutions, it considers recent data to differentiate between interleaved IO accesses, which lets us make effective death time predictions. We empirically observed that having two TCN layers of having 500 neurons each was sufficient to provide good performance. The final output layer is a dense layer consisting of softmax nodes. The number of neurons in the output layer was set to the number of open blocks within the SSD. Our proposed technique is application specific and needs to be trained on specific traces. Now, to leverage ML-DT, our model needs to be integrated to an FTL. We assume a flash-based system supporting n+1 blocks, where n blocks are assigned for user rights and 1 for GC rights. Although Oracle DT does not need a GC block, by eliminating write amplification, ML-DT cannot provide such a strict guarantee, and hence we need 1 block to absorb the rare GC rights. Each one of the open user write is assigned a death time range for each user write, and the block with the closest death time range is assigned for placing the write. The death time ranges are set according to the nth percentile of death times and the number of blocks for user rights. For example, for a system with 11 open blocks, we keep 10 for user rights and 1 for GC rights. And block 1 will store death time range in the values between 0th and 10th percentile of death time information value. Block 2 will store death time ranges in between 11th and 20th percentile and so on. Each block maintains a death time counter, which is initialized at the maximum value and is decremented after every IO. The death time range of a block, if chosen optimally, the death time counter will reach 0 when the block is full. However, as our ML model is imperfect, we need to handle the cases of non-optimal block assignments. In case if the death time counter for block reaches 0 without the block being full, it is assigned pages from adjacent two death time ranges to fill the block as soon as possible. The 3 blocks are also given additional death time given by the formula in the second bullet point. If after a programmable amount of time, the block still doesn't get closed, we assign all future IOs to that block to close that block. We keep track of, and we call it priority rights. We keep track of the number of user rights, GC rights, and priority rights, and we compute write amplification as follows. User rights by user rights plus GC rights plus priority rights. We utilized 4 baselines to compare our work: random forest, support vector machines, DNN-based LSTMs, and random predictor. To evaluate the performance of LSTMs, we replaced TCNs in our model with LSTM layers, and random forest and SVM were fed 2D input data. The table shows the comparative performance of our ML-based approach against chosen baselines using 19 dead time classes, and as one is reserved for GC writes. The LBAs without the dead time information were excluded from the trace, and we trained our models using the first 50% of the data and evaluated on the rest. The size of the input traces ranged between 0.47 GB and 43 GB depending on the source. The results from this experiment shows that our TCN-based approach consistently outperforms the other baseline techniques. The random predictor performs the worst, achieving lowest accuracy. Results from the LSTM-based approach are comparable with our TCN-based approach, that is within 5% of the accuracy. However, TCN-based models were trained 10 times faster and reduced inference latency by up to 2 times. Random forest and support vector machines perform significantly worse, achieving highest accuracy of only 56% and 61% respectively. For our work, we compared our work with 3 baselines: baseline data placement policy. First is dynamic data clustering, DAC. DAC maintains multiple open blocks, and each one is assigned a temperature. Whenever an LBA is overridden by a user-written block, it is promoted to a hotter block. And whenever an LBA is moved by GC write, it is demoted to a colder block. The second one we used was AutoStream, which leverages write frequency and recency to determine the block temperature. And it uses it to write pages into blocks of different temperature levels. AutoStream also demotes aged LBAs into cold blocks. The final baseline we use is WRSIP, write amplification reduction by clustering IO pages. WRSIP writes pages into blocks based on the block update interval, that is, elapsed time since the last write to the same LBA, in order to reduce the variance of update intervals within a block. For our experiments, we used an over-provisioning ratio of 20%, and the GC threshold was set at 0.1%. As DAC doesn't differentiate between user-written and GC-written LBAs, we provided all N blocks to DAC. But for AutoStream and WRSIP, which separates only the user-written blocks, we provided N-1 blocks for user writes and 1 for GC writes. Our approach reduces the number of GC writes due to effective placement, as we can see from the figure. On the other hand, and the priority rate overhead is minimal, accounting for less than 1% of the cases. On the other hand, DAC performs the worst, whereas WRSIP and AutoStream performs the best among the baselines, achieving comparable performance on the TPS-H benchmarks using lower number of blocks. However, they perform much worse on VDI-based workloads. Oracle DT performs best and achieves near optimal write amplification using RocksDB and VDI traces. Our approach works best for RocksDB and VDI traces where I-axis patterns are uniform and I-axis is concentrated on a few frequently occurring LBAs. The performance is comparatively worse for traces which has more uniform distribution of LBAs in the trace, for example, TPCH. Higher coverage helps in stream prediction due to greater density of input vectors fed in training and hence can produce more accurate predictions. This slide compares the performance of our approach with the baselines by varying the number of open blocks. The results show that our approach is comparable to baselines when using a smaller number of open blocks. However, as we increase the number of open blocks to between 10 and 30, our approach outperforms baselines by up to 19%, demonstrating the generalizability of our approach with increasing number of open blocks. In this section, we perform a sensitivity study to evaluate the impact of varying the number of open blocks on write amplification. For each trace, we vary the number of open blocks between 5 and 30. We see that increasing the number of open blocks increases the write amplification initially due to better organization of data within the SSD. However, as we increase the number of open blocks to over 25, we see a decrease in write amplification due to decrease in predictive performance and fragmentation of data within the SSD. This trend can be seen in the figure. To summarize, this work leveraged time-series nature of IO writes to train lightweight TCN-based models to predict death time ranges of LBAs. We presented the design of ML-DT and compared our approach with 3 state-of-the-art data placement policies. Finally, we showed that our approach results in up to 14% improvement in write amplification compared to best baseline technique and generalizes better with increasing number of open blocks. Thank you. Thank you so much for listening. Now I'll take any questions that you have.